Welcome to the video General Advantages and Disadvantages of ductile ions. Why a designer should adopt a casting instead of a forging? The main reason is the near-to-shape design. Casting is the best available technology suitable to be adopted for design of complex shapes, able to incorporating more functionalities in only one component. And this makes a process that per kilo price is typically higher than a forging process, gives to casting the chance to add the value and reduce the weight and to simplify the supply chain and avoiding weldings and weak points in a component. While a designer should adopt a spheroidal graphite cast iron casting instead of a steel casting. We have seen that in the after the last World War, when the spheroidal graphite cast iron was invented, the volume was dramatically increasing as a sign of substituting of steel forgings and steel castings. And the reason is that iron is much easier to be cast than steel because of the carbon content. Also, it is very much easier to knock in the risers, but in general also it requires less feeding than a steel casting. And all the process is more easy. Many spheroidal graphite cast irons are delivered and used as cast. So another very important recent reason is the carbon content in the austenite possible. With a steel casting or a steel forging or steel welding, any kind of steel, you can use in the austenite only the carbon that you have in the matrix. And if you need to have more, you have a special process as case hardening that can enrich the surface, but not all the volume of the casting. With iron, with spheroidal graphite irons, we have the carbon sinks, the spheroids, from where the carbon can migrate into the matrix and saturate the matrix to the maximum solubility in the austenite curve at a given temperature. That makes possible for spheroidal graphite cast iron castings heat treatments as austemporing that are not possible in the same way with steels. Another important reason is that ductile irons have a silicon content that is above the maximum used with steel. We go from 2% to 3% for normal ductile ions and up over 3% for the special grades of high silicon ductile ions. And and we know that the silicon is helping the carbon to escape from the ion combination, both in the liquid states, avoiding carbides, but also in the solid-to-solid transformation, avoiding the bionitic carbides. So for this is possible with spheroidal graphite cast irons to obtain a matrix that is called auspherite, made with stable austenite and acicular ferrite. While in steel, we adopted the same process. We obtain bainite, that means acicular ferrite and bionitic carbides. It's possible also to obtain auspheritic steels, increasing the silicon content up to 1.7 or more silicon. But this is not a normal case, this is a special case. Why? A designer will select or will remain in the well-known steel casting or steel forging or steel welding, and he will not or she will not adopt a spheroidal graphite cast iron casting instead. The main reason is something that is not in the usual calculations, but is an a priori selection to be safe in dependence of possible design errors, unexpected overloading, where we are looking for a forgiveness steel. A steel that is not breaking, but that will plastically deforming, plastically go out of use, but without separate two in parts. And this is depending from the necking behavior that is typical of ferritic steels and alloyed Kenchen tempered steels. You see here in this graph the comparison of engineering flow curve from a Kenchen tempered steel, the dotted line, and an ADI having approximately the same strength, ultimate tensile strength, and ultimate and elongation at fracture. You see how ADI, after healing, continue to strain harden up to the maximum elongation that is the same event as the maximum load, the maximum strength. While the steel, this is a wrought steel, at 5% elongation start to make a pronounced necking, and with the important restriction in area with a plastic instability deformation. This is the main difference in design from the two material families. And we need to know, well, these two different properties, and also we need to be able to measure or to rank in some way these different behaviors for a safe design of spheroidal graphite cast iron castings and an enlargement of their possibility in substitution. And what about the degenerated surface layer? We know that castings compared with the forgings needs to be considered as with a surface layer that is not the same as the bulk. In spheroidal graphite cast irons, this surface layer has a thickness of about 0.5 millimeters in green sand. And if these surfaces are in the area of the most stressed areas, we needed to consider a decrease in fatigue that we measured for one material, and we can have an idea of how the fatigue limit can decrease with raw surfaces without any treatment. But the best way, if the raw surface is in critical areas, is to machine, to remove the surface, or making a controlled shot blastings that is able to increase the fatigue surface strength at a value that is near similar to the machining surface. So these are the two procedures. So leave as it is if it is not critical, or machine or shot blast if it is in critical areas. And another question is why S-cast ferritic perlitic ductile ions are considered as brittle material. If you follow the FKM guidelines, you will see that FKM divided ferrous materials into ductile, that are typically steels, materials that show a pronounced necking, semi-ductile, that are spheroidal graphite cast irons with an elongation at fracture not below 6%, and non-ductile materials that are spheroidal graphite cast irons with a elongation at fracture below 6%. So a designer that is looking to the international standard grade definition can use as a semi-ductile material only the 507 in the wall thickness, where the 7 can be guaranteed, because when the thickness increases, the elongation is decreasing because of segregations. And it cannot use the 603 or the 702 or the 802. But the common practice indicates that typically with 600 megapascal of ultimate tensile strength in a Y25, it's typical to get elongation at fracture more than 12%. And where is the problem? The problem is that perlite ferritic ductile ions have a larger sensitivity to the wall thickness. And so if you pour a casting to get at least 600 in the maximum wall thickness, you will have 750, 800 in the smallest one. And so because of the inverse relationship between the strength and elongation, the standard make a definition that is based on the minimum hardness, where we have the minimum strength, and the maximum hardness, where we have the maximum elongation in a large range of wall thicknesses. But also considering, we are talking about the international standard, approximately all the possible commercial processes we can find. So they are defined a commodity that typically anyone in any part of the world could be able to supply. But it's not the common practice for many foundries and with controlled hardness casting design. For this, we are losing a lot of opportunities. Why S-cast ferriti perlite ductile ions are avoided by designers when possible? Not only for the reason of the poor elongation that is written in the definition, because sometimes could be also acceptable for the casting functionality. But one very important reason is the non-uniform hardness, because S-cast ferriti perlitic are produced with addition of perlite promoters that segregates at the grain boundaries. And this makes the casting to be non-uniform in all his parts when the wall thickness is different. So two ways to solve the problem are the so-called bionic design, as is defined by Geoff Fisher. That means to design a casting, this is typical for automotive castings, with the uniform wall thicknesses. So we control the Brenner hardness through a uniform wall thickness casting design. The other way, when castings are not automotive, all uniform thickness, but are general engineering castings with the different sizes of wall thickness in the same casting, there is no possibility to avoid this. So the only way to do this is not to add alloying elements, not to add perlite promoters, not to add segregating elements. So this means to produce a cast, a ferritic ductile ion, and to obtain the perlite through a very fast quenching, cooling, obtained by quenching into a soil bath. In this way, we avoid the martensite because the soil bath is above the martensite start temperature, and we get fine perlite connected with protetoidic ferrite that gives us superior strength, superior elongation, and most of all, uniform properties in different wall thicknesses, say 25, 50, or 75 millimeters. As you see in the graph, where the red bars are represented bull-eye S-cast structure with the perlitizers addition, and the violet one is representing the IDI, the isothermal ductile ion, obtained by heat treatment. Why stamped and isothermal ductile ion are not used at a very large extent? This is mainly because of the process robustness required, both in the casting process, obtain uniform castings, and the chemistry controlled castings, and also it is very important during the treatment. Now all treatment, the plants with the salts are suitable for obtaining good stamped ductile ion or isothermal ductile ion. It is very important that the austenitizing chamber guarantee a uniform temperature and inside the castings before to quench into the soil bath. And then the transfer between the austenitizing chamber to the soil bath needs to be made in a controlled, repetitive way to avoid scatter into the temperature loss during this transfer. And when we quench into the soil bath, we need that the soil bath volume is much larger than the casting weight. A typical ratio between the salt weight to the casting weight is 25:1. And the salt needs also to be agitated, and possible with the water addition. Why? Because we have a first process that is quenching when we have a transient from the austenitizing temperature to the soil tempering temperature. And this quenching needs to be very rapid because we need to avoid the paralytic nose. If the salt bath is not adequate to make a rapid quenching, we are obliged to increase the alloying content. And increasing the alloying content, we increase the segregations of elements. And segregation of elements gives a great contribution to the poor mechanical properties. So we need to have a high quenchability of our batch, of our salt batch. And then during the ausperitic reaction, we need to guarantee a fully a uniform temperature on the casting surfaces, leaving only to the internal heat transfer the equilibrium, to reach the equilibrium conditions. Then it's necessary to have a process knowledge. Austempering or isotherming is not a question of a foundry producing the casting and the treater making a treatment. It's one process. The treatment parameters are depending on the casting quality, on the nodule count, on the addition of element, on segregation of these elements. And the austempering temperature that is selected for the hardness or the grade needs to be connected with the austenitizing temperature that cannot be chosen freely depending on economic conditions, but has to be chosen in order to guarantee the maximum rate of the asperitic reaction. That is the condition to get stable austenites. Then there is a question of a process availability. Having good castings, good robust heat treatment plants, and process knowledge is something that needs a high capital investment in material, devices, as for instance heat treatment, in process control, and in people expertise. So this is the reason why starting to develop heat-treated castings in this way needs to have a minimum volume to justify this kind of investment. And this is the real reason why we are at the beginning of a long and successful story that probably will be longer than our life.